Good morning, students. Today we will discuss in this lesson the sign convention whenever light ray gets refracted through a lens. Here I have shown a convex lens and a concave lens. We will also use the sign convention in order to derive an equation to represent the refraction of light through lenses. That is the equation connecting the object distance, image distance and radius of curvature of the two surfaces of a lens. And then we will use that equation to derive the lens maker's formula. The formula or equation that helps lens makers to decide what should be the radius of curvature for the sides or surfaces when they want a lens of a particular focal length. So let us start. Real positive sign convention. As the name says, whatever is real will be considered positive. For example, if the image formed is real, we will consider the distance of the image as positive, and whatever is virtual will be considered as negative. So let us see in detail what are the points to be noted when we adopt this real positive sign convention. First of all the measurements are measured from the optical center of a lens, and if it is mirror, from the pole of the mirror. So first of all, you have to note that measurements are made from the optical center. In the case of a lens, here you can see this is the optical center of the convex lens here. This is the optical center of the concave lens. So all measurements should be made from the optical center. Now second point to be noted is that the object distance. Object distance means the distance between the optic center and the object, which is usually represented by the letter U. So U means the object distance. So object distance will be considered positive if the object is on the side from which the light is incident on the surface. So let us see this figure. The object is here and the lens is here. So where is the object? It is on the side from which the light is incident. This is the incident ray. This is another incident ray. So here this object distance U will be considered as positive. And here again you can see this is the object. It is kept on the side from which the light is incident. This is one incident ray. This is second incident ray. So here again when we consider the object distance, it should be measured from the optical center. So the object distance U will be from the optical center to the object, and whether it will be positive or negative, it's on the side from which the light ray is incident. So again here it will be positive. So the point to be noted for object distance is that whenever the object is on the side from which the light is incident on the surface, it should be positive. Now second point to be noted is regarding the image. Image distance is usually represented by the letter V, and we remember all measurements are from optic center. So here in this figure you can see that the image formed by this convex lens is here. So the image distance V is from the optic center to the image. So this distance will be V. Again here the image is formed here. The small im is the image, and therefore V will be from the optic center to the image. Now let us consider what do they say about the image distance? You can consider this in two ways. As the name suggests, whenever the image is real, you can consider it as positive, and whenever the image is virtual, you can consider it as negative. Or they say that whenever the light image is on the side from which the light ray gets refracted or reflected, it can be positive. So here look, the light rays which goes after refraction actually meets, and the image formed here is real. Therefore, V will be positive. Again, you can also see that the image is on the side from where the light rays which are reflected travel. So, the light ray gets refracted from this surface, and it is traveling to this side, and the image is in this side, so it can be considered positive. Now look at here. Are the light rays which get refracted actually meeting at a point? No. The incident ray here after refraction goes in this direction. So if someone is looking from here, that person feels that this light ray is coming from a point F. That is the principal focus of this concave lens. So for a person here, it appears that the light ray is coming from this point. The light gets diverged from this point. Also, when we consider another ray which is incident on the optic center, will pass on straight after refraction. So, for a person looking from here, even if the light rays are not actually meeting, it appears to come from here, and therefore the image formed is virtual. The light rays are not actually meeting. So the image is here, so V should be negative. In this case, V should be negative. So V should be negative. Also, by the other way, we can say that the image is not on the side from where the light ray gets refracted. So, it's on the other side. So, again V should be negative. So, again I would tell that the image distance is considered positive only when the image is on the side where the light rays goes after refraction. So here it's on the side and it can be considered as positive, but here it's not on the other side, so it should be considered negative. Now when we speak about the focal length which is usually represented by F, is the distance between the optic center and the principal focus. So here this is the optic center and the principal focus, and whenever we are considering the principal focus on the side where the light ray goes after refraction, it is considered positive. So here you can see that we are considering this side. So the principal focus is here. Therefore, we can consider the focal length which is between the principal focus and the optic center as positive. And here the image is formed here, so we are considering the principal focus on this side. This side means not the side where the light goes after refraction. So, we will consider this distance between the optic center and the principal focus as the focal length F, and it is negative. F is negative in this case. Or you can also remember in such a way that for convex lens the focal length will be positive, and for concave lens the focal length will be negative. So we have considered the sign convention for object distance, image distance and focal length. There is one more quantity of interest which is called the magnification. Magnification is represented by M. We will later learn the definition of magnification, but at this stage regarding the sign convention, I would like to tell you that Whenever the image is inverted, we consider the magnification as negative. So here, is the image erect or inverted? The object is upwards, the image is downwards, so the image is inverted. So the magnification M will be negative. And whenever the image is erect, then it can be considered as positive. Erect means upright. Here, look at the case, the object is upwards, the image is also upwards. So here you can consider the magnification M as positive. So just to summarize about the sign convention, all measurements should be taken from the optic center, and the object distance U is considered positive whenever the object is placed on the side from which the incident light ray go and meet the surface. And image distance is considered positive whenever the image is formed on the side through which the light ray, refracted light ray, will pass. The same rule goes for focal length. Focal length is considered positive only when it is on the side where the light ray goes through or goes after refraction. Here I would also like to add one thing. The radius of curvature of a surface. The radius of curvature of a surface is considered as positive when only if the center of curvature is on the side where the light ray goes after refraction. And the radius of curvature is represented by the letter R. And you know, radius of curvature is equal to focal length is equal to radius of curvature divided by 2. So focal length and radius of curvature should have the same sign. So the same rule holds for focal length, radius of curvature and image, because it will be positive only if it is on the side where the light rays goes after refraction. So that's all about sign convention. Hope it is clear to you. Now let us consider refraction of light at spherical surfaces. Here we will be considering a concave surface, but the final general equation which we derive can be applied to all types of spherical surfaces, both convex and concave. Here we will consider a light ray which is incident on a curved surface. Suppose on this side you have air and on this side you have any medium with the refractive index mu. And suppose there is an object at a point P and the light ray is incident on the surface at a point, say, S. So we have to know after refraction in which direction the light ray will go. So when it is entering from air to a denser medium, we know that it should bend towards the normal. Where is the normal? Whenever you have a sphere or a circle, if this is the center, when we draw a line along the radius, it will give the normal or perpendicular at the surface, right? So suppose for this curve or this curved surface, let C be the center of curvature. If C is the center of curvature, we know that at any point the normal to the surface will be a line drawn from C to that point. So this will be the normal. A line drawn from the center of curvature through that point will be the normal. My drawing is not that perfect, but still we can consider that. So if this is the normal, then this is the incident ray. The angle between the normal and the incident ray will give you the angle of incidence. Now after refraction, the light ray will bend a little towards the normal because this is a denser medium. So after refraction here, it will, instead of going like this straight, it will go a little bend towards the normal. So if I retrace it back, it will reach here a point, say Q. So when someone is looking at an object which is placed at point P, suppose you have a flower at point P, and if someone is looking from here, they feel that the image they see is at a point Q. The light ray is coming from point Q instead of coming from point P. So this is the angle of refraction, and the angle between the light ray in the direction of the refracted ray and the normal will be the same R, because this is the normal, this is the refracted ray. So the angle between the normal and the refracted ray here is R. So this is the same normal and this is the same direction of the refracted ray. So the angle between them also should be R. So we got the angle of incidence here and the angle of refraction here. This is the object, this is the virtual image, because they are looking from there and they feel that the image is formed here. And let this point, which I consider as the optical center, as O. Optical center of the lens is O. If it is a lens, this is just a refracting surface. Now, let me just take these three angles as alpha, beta and gamma. Now, let us consider this case and apply the general Snell's formula to this situation. What is general Snell's formula? General Snell's formula is that mu1 sine theta 1 is equal to mu2 sine theta 2. Where mu1 is the refractive index in one surface, theta is the angle in one medium and theta is the angle in that medium, maybe angle of incidence, and mu2 is the angle, the refractive index of the second medium, and theta 2 is the angle of refraction or the angle made in the second medium. So here let us substitute the values according to this case. In the first medium, which is air, we have the refractive index is equal to 1, and in the second medium we have the refractive index is equal to mu. So mu1 is 1 into sine theta 1, that is the angle of incidence, I, equal to, here mu2 is mu, so mu sine angle made in this medium is R. Or from this equation, I can write mu is equal to sine I divided by sine R. Here I have taken sine R to this side, multiplied by 1, so we don't have to write it. Now, here you can see that the angle of incidence and the angle of refraction are very small, because we consider a small aperture, and even the drawing shows that the angle of incidence and angle of refraction are very small if the object is at a distance, at an appreciable distance from the center of curvature. So in this small aperture case, we can consider angle of incidence and angle of refraction as very small. What happens when the angle is very small? What about sine theta when theta is very small? You know that sine 0 is equal to 0, and similarly if theta is small, sine theta will tend to give you theta. So this is a trigonometric consideration where whenever theta is very small, we can consider sine theta as theta. So here Since I and R are very small, I can consider the approximation. Instead of sin I am writing I, and instead of sin R, I am writing R. So here we have considered the trigonometric approximation that whenever the angle is small, sine of that angle can be considered as equal to the angle itself. So here I have I by R is equal to mu, or I can write mu into R is equal to I. Let me consider this as equation 1. Now let us look at the figure. From the figure we have just marked angles alpha, beta, gamma. Now is the case where we use those three angles. We are trying to express both R and I in terms of alpha, beta and gamma. For that, look at the triangle SPC. I will draw it separately because this figure is small and congested. So let me draw it separately. I am drawing triangle SPC. So triangle SPC. Okay, and we have the angle between PS and PC as the angle of incidence. Incident ray and normal. So this is angle of incidence I. And we have drawn this angle as alpha. And here you have angle gamma. So when you consider this triangle, gamma is the exterior angle and I and alpha are opposite interior angles. So by the property of a triangle, I can write gamma is equal to alpha plus I. So let me write from this consideration or considering triangle SPC, gamma is equal to I plus alpha, or I is equal to gamma minus alpha. So I got an expression for I in terms of gamma and alpha. Now let me consider another triangle, triangle SQC. So I am drawing this separate here, triangle SQC and SQC. Again you have SQ is the direction of the refracted ray and SC is the normal. So the angle between these two is I. And you also have this angle marked as beta and this angle is gamma. Again, when you consider the triangle SQC, this gamma is the exterior angle, R and beta are interior angles. So we can write the external angle as the sum of the two internal angles. So from triangle SQC, I am writing gamma as equal to R plus beta, or in other words, I can write R is equal to gamma minus beta. So I got an expression for I and R, which I will be substituting in equation 1. So I hope these two considerations of triangles are clear to you. Let me rub them. And now let me put I and R in equation 1. So put the expressions for I and R in equation 1. The equation 1 will become mu times gamma minus beta equal to I is gamma minus alpha, gamma minus alpha. I want to bring the terms containing gamma to one side. So when I take mu into the brackets, this will be mu gamma minus mu beta is equal to gamma minus alpha. So I am taking minus alpha to this side, so it will become plus alpha, and mu gamma to other side, so it will become minus mu gamma. So alpha minus mu beta is equal to gamma minus mu gamma, or alpha minus mu beta is equal to, when I take gamma outside, gamma times 1 minus mu. Now, you must have learned when you studied the SI units in the second or first chapter of grade 11, the definition of SI units. What is the SI unit of angle? Radians. So how is a radian defined? When you have a circle and you have an angle theta, if angle theta is represented in radians, if this is the arc length S, and this is the radius r, theta, the angle in radians, is defined as arc length divided by radius. Remember that? So I am going to use this concept, the definition of radians, to express the angles alpha, beta and gamma. So look at alpha. So when you consider this part PSO, similar to this, alpha is the angle and the arc length is OS and the radius is PO. So I am going to express alpha as OS by PO. So alpha is equal to OS by PO minus mu times. What will be beta when you consider this angle beta? It's also part of a sphere having arc length OS and the radius OQ. So I can express beta as OS, arc length, divided by radius OQ. So mu times OS divided by QO. I represented PO, but it is better to write it as OP, from optic center to the object, right? So here OQ is equal to, instead of gamma, when we look at this part, we get the arc length OS and the radius OC. So I can represent this as OS by OC. So here what did we do? We represented each of the angle using the definition for a radian. The angle represented in radian is equal to arc length divided by radius. So let me rub this part. Now look at this equation. OS is common in every term. So I can cancel OS out, and also OP. Here at P we have the object, and at Q we have the virtual image, and at C, which is the center of curvature, so the distance between O and C will be the radius of curvature R. So I am going to express, instead of OP, the object distance U, and instead of OQ, the image distance V, and I will also consider the sign convention, and also OC will be expressed as R, the radius of curvature. So here I have, I'm sorry, I forgot to write 1 minus mu, which is here 1 minus mu. So here OS is cancelled throughout, so we have 1 by OP is what? Object distance U, minus mu times, what is here? You have OQ. So the image is here. So if we consider this distance as V and the image is virtual, so V will be negative, and also it's not on the side or the surface from where the refracted ray goes. So here we can consider image as minus V equal to, here I have 1 minus mu divided by, what is OC? OC is the radius of curvature. Is R positive or negative? R will be negative. One reason, it is not on the side where the light ray goes after refraction. Second reason, see the surface, it is concave in nature, and we know for the concave lens, focal length and therefore radius of curvature are negative. So due to both reason, I can put it as minus r. So here there is a minus and a minus in the denominator. So this will be equal to 1 by u plus mu by v equal to, there is a minus sign in the denominator, which if I took to the numerator, I can write it as, instead of 1 minus mu minus 1 whole divided by r. So this is the equation we come up with when we consider a particular case where the light ray from air goes to a medium having refractive index mu. This is because we consider the refractive index in the first medium mu1 as 1 and the refractive index in the second medium mu2 as mu. Now instead of 1, if we substitute mu1 and instead of mu, if you substitute mu2, this will become a general equation which will be applicable for refraction through any media. So whatever be the media, whether it is refraction from a rarer medium to a denser medium or from a denser medium to a rarer medium, we can make a generalized equation which will be applicable. So instead of 1, I write as mu1 by u plus, instead of mu, if I write mu2 by v is equal to, instead of mu2 minus 1 mu1 divided by r. So this is the general equation for refraction at spherical surfaces, that is mu1 by u plus mu2 by v is equal to mu2 minus mu1 by r.